This is very simple problem based on analytical techniques. An ion complex, the general formula is FeL6 2 plus, ion is in +2 oxygen state. Here L is neutral monodentate ligand. Since 6 ligands are there, it should be monodentate only, and it is neutral ligand. Catalyzes the oxidation of dimethyl sulfide by perbenzoic acid. The formation of the organic product in the above reaction can be monitored by. So this is the reaction. Dimethyl sulfide is oxidized by perbenzoic acid. I take like this. R will be phenyl. The most common perbenzoic acid we use is metachloroperbenzoic acid. The product what we get is dimethyl sulfoxide. Suppose if you add excess of perbenzoic acid, this can be further oxidized to give dimethyl sulfone. Even this reaction is possible with hydrogen peroxide. So in the presence of peroxide, dimethyl sulfide is converted into sulfoxide, that is further converted into sulfone. The formation of this product can be confirmed by or monitored by: first one, gas chromatography; second one, cyclic voltammetry; third one, electron spin resonance; fourth one, fluorescence spectroscopy. So it is very simple. You can go for gas chromatography. The reaction mixture can be injected into the column. Here there is no metal. All are organic compound. All are soluble in the solvent. So they will be dissolved in the solvent, or the reaction mixture will be taken, that will be injected. There will be some RT value for dimethyl sulfoxide. If it is observed, if that particular RT is observed, then you can say that dimethyl sulfoxide has formed. Similarly, there may be some RT value for dimethyl sulfide. Say you get only that particular RT value. That means dimethyl sulfoxide has not formed. Dimethyl sulfide is basically gas. But dimethyl sulfoxide is liquid. We convert the reaction mixture into the gaseous phase, and that is injected. That's why it is referred as gas chromatography. In HPLC, the liquid sample itself will be injected. Okay, what about cyclic voltammetry? Cyclic voltammetry is used to find out the redox reaction. When there is transfer of electron, that can be identified by cyclic voltammetry. The oxidation peak and reduction peaks will be observed. But here there is no metal, no electron is transferred, so this cannot be used. Electron spin resonance. There should be some free radical. The organic compound, if there is any free radical or any unpaired electron, we can go for electron spin resonance. But here there is no unpaired electron or no radical. Last one, fluorescence spectroscopy. The compound, whatever we have discussed here, dimethyl sulfide or dimethyl sulfoxide, dimethyl sulfone, they don't have fluorescence property. Because of that, we can't use this also. The oxidation state of the metal ion in the catalyst can be detected by ion is used as catalyst. During the reaction, the active species may be Fe2 plus or Fe3 plus. Ion can exist in +2 oxygen state as well as +3 oxygen state. Both are stable. In fact, 3 plus is more stable. Now the question is, which one will involve in the catalysis? To predict that, which method can be used? The given options are atomic absorption spectroscopy, mass Bayard spectroscopy, HPLC, gas chromatography. As soon as you see these two, both are chromatography techniques, they cannot be used to find out the oxidation state. They can be used to separate the compounds. Also in HPLC as well as gas chromatography, generally we don't inject the metal. They may not be soluble, they may get stuck in the column, they may not come out of the column. The column is very expensive. The column, whatever we use in column chromatography, that is very cheap. But whatever we use in HPLC and gas chromatography, they are very expensive. So generally what we do, we filter and we take only the solution. If your compound is not soluble, say your metal is insoluble in the solvent, in that case it is not at all possible to inject into the column. We can find out how many compounds are present in the given solution or the reaction mixture. That only you can find out, not the oxidation state of the catalyst. So based on that, we can eliminate the two options very easily. We have atomic absorption spectroscopy and mass Bayer spectroscopy. These are the remaining two options. Atomic absorption spectroscopy also is a wrong answer. It is not possible to find out the oxidation state by atomic absorption spectroscopy. Simply we say as AAS. We can identify the presence of certain metal, at which wavelength it absorbs the light. We can find out the metal present in that. We can't find out in which oxidation state it is present. Finally, we are left with mass Bayer spectroscopy. It is possible to find out the oxidation state with mass Bayer spectroscopy. This is the correct answer. Fe2 plus and Fe3 plus, they will have different isomer shift. The mass Bayer shift for Fe2 plus and Fe3 plus will be different. If you have the reference value, then you can compare and you can identify which species is present in the reaction mixture. So isomer shift can be used to identify the oxidation state. Further, there is possible quadruple splitting. The signal, whatever we have got for Fe2 plus or Fe3 plus, that can be splitted, that is referred as quadruple splitting. Simply we say as QS. The signal, whatever we have got for Fe2 plus or Fe3 plus, can be splitted, that is referred as quadruple splitting. That is generally happen when there is electric field gradient. When the electron density is not equally distributed, that time there will be electric field gradient, we will get quadruple splitting. For example, let us consider Fe2 plus and it is, say it is high speed. The simplest example is Fe CN6 4 minus. Here ion is in +2 oxidation state. Since the field is strong, since the ligand is strong, the 6 electrons will be placed like this. Here all the T2G orbitals are symmetrically filled. These orbitals will be directed in between the axes. So the electrons are equally filled or symmetrically filled around the metal. Suppose, say it is Fe3 plus. The distribution will not be uniform. There will be only 5 electrons. In one axis or in one direction, the electron richness will be less. So the electron density will not be uniform. So in that case, there will be electric field gradient. That will result in quadruple splitting. So based on isomer shift or quadruple splitting, it is possible to predict the oxidation state of the metal.